Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. This is going to be the first video in which we talk about Chapter 10, which is going to deal with parametric curves, and specifically how we do calculus on different situations of parametric curves. We're going to talk about both how to deal with parametric curves in the classic sense in terms of defined as time, but we're also going to talk about parametric curves in terms of polar coordinates, which is another way of quote-unquote parametrizing situations. Okay, so first in chapter 10.1 and 10.2, we're going to deal with parametric equations. And first we're going to talk about what a parametric equation is in general. Essentially, there's a lot of functions that we can have, well not functions, a lot of curves that we can have on a Cartesian plane that aren't necessarily functions because they fail the vertical line test. Anything that fails a vertical line test, for example, something like this, would not be considered a function because it fails the vertical line test. I have multiple different y values for a certain x coordinate. And you can also have it fail the horizontal line test for functions defined with x equals. In these kinds of situations, it'll be more beneficial to define the curve parametrically, which means we define both x and y separately in terms of some other variable. That variable we very often will use is the variable t, which we usually consider as time, in terms of how much time we have elapsed when traveling along this curve. The best way to think about a parametric curve is really, if I have this curve up here again, I'm starting at some point, and then I'm progressing through. And over time, as I'm walking along this, I want to see what happens to x and what happens to y. Overall, that means that this is going to be split up into two different functions. One function of x in terms of t, and another function y in terms of t. And both of these are going to be their own functions. That's the overall goal here. Split x in terms of t and y in terms of t. Doing so is easier said than done, and a lot of the operations we have in calculus we need to adjust because we have a different set of equations to work with. However, in this section, we're going to just start with working with parametric equations by sketching the graphs inputted by values of t. So we're going to be putting values of t in to sketch the graph, and then we're going to see if we can come up with the Cartesian form of those equations as well. And that usually involves simply isolating t from one of the equations, one of the x equals ft or y equals g of t. Try to isolate t if possible, and then plug into the other function. Oftentimes, we're going to try to make our goal to get it in terms of y equals f of x, a familiar form, but if that is not possible, then so be it. Okay. We'll also have in some examples, before I move on, we'll have in some examples some specific bounds of t, in which case that'll tell you what bounds you need to work with. But if you're not given bounds, or if it's more open-ended, then you need to consider what would also happen if I were to continue on in that direction. Okay. So for the following examples, what we're going to do is we're going to sketch the parametric equations as well as the direction of the curve. That's going to be important. And we'll also determine a Cartesian equation represented by the set of parametric equations. Now, we're going to also try to make our goal to get it in terms of y equals if possible, but if not, then so be it. Okay, first we have x equals t squared, y equals natural log of t. Now, if we're going to try to solve this in terms of graphing it, all we really need to do is plug in values of t, and specifically we want to work with ones that are simple to us. Notice in this situation as well that natural log is in one of the functions. I have y is equal to natural log of t. That is going to limit what we can plug into t. I don't see an absolute value, so I should not assume it to be. And what I know about natural log is that that will accept values that are positive. Because if I were to set, for example, t equal to 0, x would be 0, but y would be natural log of 0 approaches negative infinity. After that, though, we can get more specific values. So maybe I plug in a t of 0.5, and I get 0.5 squared is going to give me 0.25, or 1/4. And then if I do natural log of 0.25, I get negative 0.602. Oh, sorry, that was just a log. Negative 1.386. And then I just try to keep putting in numbers that are easy. This I just kind of wanted to see where the values were going. But then I could just start plugging in whole numbers. So 1, 2, 3, and then I should start to see a general trend as I continue. So let's plug in 1. 1 squared is 1. If I plug in 2, 2 squared is 4. 3 squared is 9. The x values are relatively simple. But then 1 here, natural log of 1 we know is 0. If I do natural log of 2, I get 0.693. And then if I do natural log of 3, I get 1.098 or 1.099. Now I have x and y coordinates I can start to plug in. So I'm going to do so on this graph here. For the first one, it has an infinite bound, so we'll deal with that in a moment. But I have, for t of 0.5, I have x is 0.25, which would be around here. And then y is negative 1.38, so maybe around there. Then I have 1, 0, which is right there. And then 4, natural log of 2, which is 0.693, so around there. And then when I have 9 for x, I have 1.09. So it is continuing on in this fashion. And then I also see if x was 0, which is the y-axis, I have y as negative infinity. So it seems to be going like this. Connecting those points. Now what is also important is keeping track of the direction of these points. As t increases, I have a specific direction in mind. So I'm going from 0.25, negative 1.386 to this point, to this point. So that means I'm also going to include arrows so I know the direction of travel. That is going to be important, particularly when I'm graphing something like a particle that is in motion. So always when you draw a parametric graph, you also include the arrows in terms of the direction of travel. Now, solving for this isn't too bad now. We have the graph done, but now what we want to do is try to make this into a Cartesian equation. Again, our goal is going to be to try to make it into y equals f of x if possible. And thankfully, I can isolate t with the variable of x. I could take x equals t squared, square root both sides, and simply have that t is equal to root x. Therefore, when I take my function of y equals natural log of t, I can plug in square root of x into t, and I get y equals natural log of the square root of x. Or you can also write that's x to the 1/2, which you could also pull out front. You could say that's 1/2 natural log of x. It's also the same thing. And that looks about right. This does just look like a natural log function. So everything seems okay there. This can be represented with a normal Cartesian form. Alright, so it's just a nice and easy one just to get started with some parametric curves. The next few are going to be a little bit more weird. We have here in example 2, we have x equals t cubed plus t. We have y is t squared plus 2. And in this case, we actually have bounds on t. We have negative 2 up to 2. Note the previous one we did not have bounds, so that meant when we finished drawing our points, we continued where the line would go in both directions. But here we have bounds. That is, on one side, easier, but also we do need to really be careful when we make our arrows. That means we have negative 2, negative 1, 0, 1, and 2 are probably the easiest ones to plug in. And I should be able to find the x and y coordinates relatively simply. Negative 2 cubed is going to give me negative 8 minus 2 is negative 10. There'll be negative 1 minus 1 is negative 2. 0, 0. 1 plus 1 is 2, and 8 plus 2 is 10. For y, negative 2 squared is 4 plus 2 is 6. Negative 1 squared is 1 plus 2 is 3. 0 plus 2 is 2. And I'm going to get the same things again, 3 and 6. So those points are relatively simple to do. But again, keep in mind the direction of travel. When we plot our points, we're going to also have to keep in mind arrows. So x of negative 10, y of 6, it's kind of off here. But we see negative 2 and 3, I could plot that pretty easily. I just want to make a standard graph here. So negative 2 and positive 3 would be roughly here. And then I have x of 0, y of 2, 2 and 3. And then they start to increase more and more. So let's say that 10 and 6 was somewhere here then. So I'm just going to put negative 10 and 6 and 10, 6. So I'll say that this is negative 10, 6, and this is 10, 6. When I connect all these points together, I get basically a U shape. And notice that I'm going to stop at those points. I am not going to continue and say that it continues past here because we have a limit on t. We're not continuing considering t going on in infinite directions. Furthermore, I need to make sure my path of travel is correct. So negative 10, 6 to negative 2, 3. That means I should be going in this direction of travel. That is important because this curve could be going the exact other way. So we do need to be careful with that. All right, so that would be the equation of this curve. Or that would be the graph of this curve. The equation is not going to be as simple. If we notice here, we have x equals t cubed plus t. That means it's going to be relatively difficult to get t by itself completely. It'll be a lot easier actually for y to get t by itself and then plug in. So that's what we're actually going to do here. So we're going to take y equals t squared plus 2. Do that in black. So y equals t squared plus 2. We'll solve for y. Y minus 2 equals t. We just take a square root to finish that off. And then when we have x equals t cubed plus t, we should be able to take this square root of y minus 2 and plug that into both t cubed and also this t. That is going to give me x equals y minus 2, that's the square root to the third power, so that's 3/2, plus y minus 2, and I'll say to the 1/2 just to keep consistency between these. And that would be my equation of this graph. Note that it's difficult to get y by itself even when looking at this formula. Okay. After that, we're going to have some that involve some trig functions. So I have cosine, sine, and the next few I'm going to have sinh and cosh, and also tangent and secant. When you have trig functions, these are a little bit trickier, but at the same time not. You just need to keep in mind a lot of your trig identities. Still, though, we're just going to plug in values to find t. And notice I don't have bounds here, so I could plug in anything. But I want to keep something that's easy for me. I'm not going to do -1, -2, or, sorry, not going to do -2, -1, 0, 1, and 2 here. That'd probably be good for algebraic. But here my functions are sine and cosine. So instead, let's deal with values that are pretty easy. First, I'm going to start with 0. I usually like to work with 0, maybe above and below it. But I should just be able to do anything. So I'm just going to use some values from maybe the first and second quadrant. So I'll use 0, pi fourths, pi halves, 3 pi fourths, and pi. Now, if you took trigonometry, you probably did this a few times as well, and you probably really used the main ones. So 0, pi halves, pi, 3 pi halves, and 2 pi. These would be all well and good, but the problem here would be sine of 2t, which would double all of these, make them like this would make them 0, 2 pi, 3 pi, and 4 pi. And all of these, sine of all of those would be 0, so not really helpful. So instead, we divide them all by 2, and we have the values with fourths in them. Then if we plug those in, we'll actually get more, well, interesting values for sine and cosine. Something that will actually tell me what this looks like. Now, these are not all the points, but we're going to continue this trend because we do not have bounds on t. If I plug in 0, cosine of 0 is 1. Sine of 2 times 0 is still 0. Cosine of pi fourths, that's root 2 divided by 2. Sine of 2 times pi over 4, which is sine of pi halves, that will give you 1. Cosine of pi halves is 0. Sine of pi halves times 2 is pi is 0. Cosine of 3 pi over 4, that's over in quadrant 2. Cosine is negative over there, so it's negative root 2 over 2. 3 pi over 4 times 2 is 3 pi halves. That's sine of 3 pi halves. It'll give you negative 1. And cosine of pi will give you negative 1. Sine of 2 pi will give you 0. Alright, note again that these are not all of it, but this should give me an idea. And after I graph this, you may even recognize this, particularly if you did take trig. So let's put my points together here. I have 1, 0. So that's around here. I have root 2 over 2 and 1. Root 2 over 2 is between 0 and 1. So somewhere around here maybe. And then I have 0. And then I have the negative equivalent of that. And then up to negative 1, 0. So if I connect these, I have a curve that kind of looks like sine, actually. Now, at this point, you should probably be wondering, okay, well, is this going to continue like sine? Or is it going to do something else? So, when in doubt, go ahead and check another point. If I do 3 pi fourths pi, the next one would be 5 pi fourths. If I plug in 5 pi fourths into cosine, that's over in quadrant 3. That's still negative root 2 over 2. 5 pi fourths times 2 is 5 pi halves. It's the same thing as pi halves. So it'll give you 1. And that point, let's do that one in another color so you can identify that more specifically. So this point is at negative root 2 over 2 and 1. That's curling back. What this function is actually going to do is it's going to curl back like this and come back in and make this shape. So it makes an infinity symbol, basically. This is known in trigonometry as a lemniscate. That's what we just graphed here. Now, what we're going to do is try to make a Cartesian form of this. However, that's going to be a little bit more difficult. What you can do, though, is apply what trig identities you know. Particularly sine of 2t. We know that one. That's a double angle identity. I should be able to rewrite sine of 2t as 2 sine t cosine t. So I can say y equals 2 sine t cosine t, and I just need to find out what both sine t and cosine t are. Well, cosine t is just x. That's easy. But sine of t is not so much. However, if I'm basing it off of x equals cosine of t, I can work with something that we did before when we did trig substitution and think about this triangle that this would make with an angle of t. The angle of t would make cosine, which is adjacent over hypotenuse, would be x and 1. The opposite would be the square root of 1 minus x squared. And so we get that sine of t is opposite over hypotenuse is the square root of 1 minus x squared. So then we can say y equals 2, I'll put the x first, and then the square root of 1 minus x squared. So that would be our function. Now, if you were to actually plug this in, what you would actually get is just the first half that we got. Basically what we got from 0 to pi. To get the rest of that, notice that the rest of the Lemniscate would be flipped over the x-axis, really. And that is because we have this square root, which technically has a plus and minus on it. So really, we made half of the graph. So this would be one of the formulas with this positive square root. But then the other one would be y equals negative 2x square root of 1 minus x squared. So both of those together would make our overall formula. But this first one should suffice. Alright, so remember your trig identities, those can still come in handy. Speaking of, let's do another one, and we're also going to do an identity from hyperbolic to try to figure out this one. If you haven't already, I recommend pausing the video on example 4 and 5 and see if you can figure those out, particularly when you're trying to find the equation of this one, because this one's going to be a little bit more creative. Okay, well, we have x equals sine t and y, or sinh t, and y equals cos t. And we have t is greater than or equal to negative 1. Alright, well, that means that we're going to do negative 1, 0, 1, 2, and 3 would probably be good enough to figure out what's going on here. But sinh of negative 1, I don't know necessarily off the top of my head, neither do I know cos of negative 1. But we do know the exponential equivalents of each of these. We know that x is sinh, so that means that's e to the t minus e to the negative t over 2. And we know y is cos, which is e to the t plus e to the negative t over 2. We can use these formulas to find what x and y coordinates are going to be. For example, if I do negative 1, what I get is e to the negative 1 minus e to the negative 1, so minus e really, or e to the 1. And then if I divide that by 2, I get about negative 1.175. Same thing for y. In this case, I'm just going to get a plus in between those two instead. So e to the negative 1 plus e to the 1. And if I divide that by 2, I'll get a positive number. I'll get 1.543. We can continue on in this fashion and construct x and y by just plugging in values of t into this. I'm going to pause at the moment, and I'm going to fill out the rest of these values. Okay, so I've filled out the rest of this. Now, we already know what's really going to happen with sinh and cos here anyway. We know that as x gets larger and larger, really this part is going to go closer and closer to 0. This part is going to go closer and closer to 0. So this is really approaching e to the t over 2. This one's also approaching e to the t over 2. That's why we're starting to see a lot of the same numbers for x and y. Alright, but aside from that, we have the rest of our values here, and we should be able to plot these. Alright, keep in mind the order. So negative 1.175 for x and 1.543 for y. So around here and around there. Then 0, 1. Then about the same points, but in the positive direction, so around here-ish. 3.623 and 3.7, so a little bit more than 3 halves each. Up, be a little bit further there. Around there. And then I have the point up in 10. And notice that t is greater than negative 1, so that means we're going to continue past in this direction. And so what I'm going to do is start at this initial point and draw my line. I'll do this in blue. Draw my line going through all these points off in this direction. And this should be approaching that e to the t over 2, really. Which is starting to look like that. Notice, however, that I keep the arrows, if I notice that I'm going in this direction, I'm keeping the arrows continuing on this way, because this is where t approaching infinity is going to go. But I do not continue the line going this way. I leave this part gone. And that's because strictly t was supposed to be greater than or equal to negative 1. So this is the first point that we plot at, basically the initial point of my particle, if I want to think about it in a physics way. All right. Now, if I'm trying to get this in terms of just one function, I need to think about what we do know about these functions, sinh and cosh. Now, we did a lot of identities back in 3.11 for sinh and cosh, but we had one that's very particular that relates both sinh and cosh and doesn't have another function in it. We had a lot of them that result in just e to the t or something, but we did also have one that looked a lot like the Pythagorean identity that did not have another function of t, that only involved sinh and cosh itself. That identity that we had was cosh squared of t or x or theta, whatever you're working with, minus sinh squared of t equals 1. If I know that cosh is y, then cosh squared is y squared. Sinh is x, so sinh squared is x squared equals 1. So we have y squared minus x squared equals 1. What is this creating? Well, what are these called? These are called hyperbolic sine and hyperbolic cosine. So this is creating a hyperbola. Okay. One more. All right, tangent squared t, y equals secant t. So again, we don't have bounds in this case. So it means we could do anything. So let's do convenient ones maybe. Particularly for tangent and secant, that's going to be a little bit tricky. I know that 0 is fine for both of these, so I should be able to use 0. And I know that around that is also okay. So maybe let's do negative pi halves up to pi halves. And those also negative pi fourths and pi fourths. I don't want to just use the pi halves multiples because that's not really good for secant. A lot of those will end up either being 1 or undefined. So I want at least something else. And same thing for tangent. When I approach negative pi halves and pi halves, I'm going to get infinities. Specifically, for x, I have a tangent of negative pi halves. If you remember what tangent squared is doing, as you approach negative pi halves, tangent would be approaching negative infinity, but it's squared, so that means I'm approaching positive infinity. And likewise with pi halves, tangent of pi halves is positive infinity, squared is also positive infinity. So those are pretty easy. Same thing with secant, as I'm approaching negative pi halves being between quadrant 4 and quadrant 1. So if I'm thinking about this like this, I'm approaching pi halves. Secant then, which is 1 over cosine. And cosine is going from 1 and it's getting closer to 0. So if I'm approaching negative pi halves, that means that this is approaching 1 over 0, but that 0 is positive itself. So it means this should also be approaching infinity. And the same is true for pi halves. Now we just need to know the middle points, and those are pretty easy. So really the infinite bounds were the question here. Negative pi fourths into tangent. I know that tangent at pi fourths is 1 or negative 1 squared will give me 1. Same thing for pi fourths. This one technically would be negative 1 squared. 0 into tangent, that's going to give me 0. That'll give me sine over cosine, so 0 over 1. And if I do secant of negative pi fourths, that's over in quadrant 4, where secant is positive. Instead of getting root 2 over 2, which is cosine, I'll just get root 2. And that's the same thing I'll get for pi fourths. But for 0, secant of 0 is 1, just like cosine. So I have my points here. I see infinity, infinity, and I have the other points I should be able to plug in. So negative pi fourths is basically 3 divided by 4, more or less. So about 0.75-ish. And I have, well, I don't need to know that. For x, I have 1. And for y, I have root 2. Root 2 is less than 1. Oh, sorry, it's more than 1, but less than 2, because that would be root 4. So 1 and root 2 would be right there-ish. I also have 0, 1. And then I have 1 root 2. Which is, well, the point that I just made here. So I already basically have these points. Now I know, basically what that means is that I'm progressing from 1 root 2 back to here. And then once I get to that point, I'm turning back around. So overall, it's like approaching here, but then it's approaching back. And this is going to be going off in that direction. So I'm approaching there. But let's say I approach in this direction. Is that the entire curve? Well, again, we can check some other things. We haven't really checked on the other side of these infinities. So let's check at least one more of those. Let's do 3 pi-fourths and maybe just pi. See what happens on the other side of these. Well, if I do 3 pi-fourths into tangent, again, that's going to give me -1 squared is 1. And pi for tangent is going to give me another 0. So not that interesting. But for secant of 3 pi-fourths, that's in quadrant 2. And secant over there is negative. So that's going to give me negative root 2. Likewise, pi, secant of pi, is going to give me -1. So that means what I'm going to get here is actually 1 negative root 2, which is around there, and then 0 -1. So maybe let's put that around there, yeah. So basically what I'm actually getting is this, basically a claw, but it has this like discontinuity here where there's nothing happening in the middle there. So this overall is the graph of tangent squared t, y equals secant of t. A little bit of a weird one. Now if we want to isolate this variable, then we can work with this in a couple different ways. However, to approach it in a different way than we did before, what we can simply do is just define one of them. Simply, hopefully, y, because that's usually the one we want to find. And then plug in for the other. So we can say x equals tangent squared t. Okay, well that means that square root of x equals tangent of t. And therefore t is equal to arctan of square root of x. Okay. Now what arctangent means that if I have some unknown angle measure, that angle measure in this case being t, the tangent of that will give me a ratio of root x over 1. Okay, well that means opposite over adjacent, that's root x here and 1. And therefore the hypotenuse would be the square root of x squared plus 1 squared, or just square root of x plus 1. What I then want to find is y equals secant of t. Secant of t is hypotenuse over adjacent. So that's going to be square root of x plus 1 over 1, or just y equals square root of x plus 1. And then to get the other one, the one on the bottom, that gives us also y equals negative root x plus 1, for the reason that we had earlier as well. That square root can be plus or minus. So that's what we overall graphed here. Just basically the square root of x plus 1. All right, with that said, that's some examples of parametric equations and how to graph those, how to both graph those and how to solve for the Cartesian form of the equation if possible. If you have any questions, feel free to put those in the comments below or ask your instructor directly. But with that said, I hope you have a nice day.